Okay, this is the video lecture for the Respiratory System Laboratory. What I have posted here on the screen is the PowerPoint.
Your goals for learning are to relate Boyle's law to ventilation,
some are best shown on
to identify the
models,
muscles
others,
used during ventilation,
to understand how volume changes in the thoracic cavity cause pressure changes that lead to airflow,
to identify factors which influence airway resistance and lung compliance. Here's what you need to know: the location of the visceral and parietal pleurae and the pleural cavity. The visceral pleura and the parietal pleura enclose each lung in a separate sac. The frosty layer you see here covering the lungs is the portion of the parietal pleura that lines the anterior thoracic wall. Click a lung to remove the anterior part of the parietal pleura.
Keep it simple, and this whole region here is the nasal
Now that the anterior portion of the parietal pleura has been removed, we can see the visceral pleura, which covers the surface of the lungs, and the cut edges of the parietal pleura. The pleural cavity is an extremely thin, slit-like space between the pleurae, separating them by a thin layer of pleural fluid. The pleural fluid assists in breathing movements by acting as a lubricant. Click a lung to see the posterior portion of the parietal pleura. In this view, the lung has been removed to show the posterior portion of the parietal pleura. Recall that the parietal pleura lines the mediastinum, the superior surface of the diaphragm, and the inner thoracic wall.
Touched, for example, with your finger, it promotes a gagging reflex, or if food comes back there prior to our
Now let's continue to follow the airflow as it enters the lung. Your goals for learning are: in order to understand ventilation, we must first look at the relationship between pressure and volume. Pressure is caused by gas molecules striking the walls of a container. The pressure exerted by the gas molecules is related to the volume of the container. Click the sphere to see how volume affects pressure. This large sphere contains the same number of gas molecules as the original sphere. Notice that in this larger volume, the gas molecules strike the wall less frequently, thus exerting less pressure. Click the sphere to see what happens when it is decreased in size. In this small sphere, the gas molecules strike the wall more frequently, thus exerting more pressure. Notice that the number of gas molecules has not changed. These demonstrations illustrate Boyle's law, which states that the pressure of a gas is inversely proportional to the volume of its container. Thus, if you increase the volume of a container, the pressure will decrease, and if you decrease the volume of a container, the pressure will increase. Click the buttons to change the size of the sphere and see the demonstrations again.
And then the next part of the throat is the oropharynx, starting at the tip of the uvula down to this structure. This blue structure is a fold of cartilage called the epiglottis. So from the tip of the epiglottis, so we're starting right about here, to the tip of the uvula here. So this region,
the volume of the thoracic cavity is changed by muscle contraction and relaxation. Take a few seconds to notice the movements of your chest during your own quiet breathing.
Looking at the diagram, the oropharynx then would be again from the tip
during
of the
quiet inspiration,
here,
the diaphragm and the external intercostal muscles contract, slightly enlarging the thoracic cavity. Notice how the diaphragm flattens and moves inferiorly, while the external intercostal muscles elevate the rib cage and move the sternum anteriorly. These actions enlarge the thoracic cavity in all dimensions. As we learned from Boyle's law, increasing the volume decreases the pressure within the thoracic cavity and the lungs. Click either illustration to repeat inspiration.
Swellings on either side in the back of the throat. Those are the palatine tonsils. So That's what is shown right here. And in
Quiet expiration is a passive process in which the diaphragm and the external intercostal muscles relax, and the elastic lungs and thoracic wall recoil inward. As the diaphragm relaxes, it moves superiorly. As the external intercostal muscles relax, the rib cage and sternum return to their resting positions. These actions decrease the size of the thoracic cavity in all dimensions, and therefore increase the pressure in the thoracic cavity. To see both inspiration and expiration as a continuous cycle, click the cycle button.
This is the laryngopharynx. Looking at the model, that would be from the tip of the epiglottis here down to here where we see the larynx beginning. So it's this region from
Deep breathing uses forceful contractions of the inspiratory muscles and additional accessory muscles to produce larger changes in the volume of the thoracic cavity during both inspiration and expiration. During deep inspiration, the diaphragm and the external intercostal muscles contract more forcefully than during quiet breathing. Additionally, the sternocleidomastoid and scalenes contract, lifting the rib cage higher. These actions further increase the volume. As we learned from Boyle's law, this decreases the pressure within the thoracic cavity. Deep or forceful expiration is an active process. The internal intercostal muscles depress the rib cage, and the external oblique, internal oblique, transversus abdominis, and rectus abdominis muscles compress the abdominal organs, forcing them superiorly against the diaphragm. These actions can dramatically decrease the volume and further increase the pressure within the thoracic cavity, producing forceful expiration. Click the illustration to see deep breathing. Contracting muscles are highlighted in blue.
Covers the opening into the larynx, and that's the epiglottis. So this beige kind of tongue-like looking structure here is the epiglottis. So looking back here, again, this is the epiglottis. And this is the larynx.
Now let's look at the specific pressure changes that occur in the lungs during breathing. For reasons described later, the lungs closely follow the movements of the thoracic wall. The pressure within the lungs is called the intrapulmonary or intraalveolar pressure. Between breaths, it equals atmospheric pressure, which has a value of 760 millimeters of mercury at sea level. When discussing respiratory pressures, this is generally referred to as zero. Click the lung to see intrapulmonary pressure changes during inspiration. Observe the changes on the pressure gauge and the graph. During inspiration, the volume of the thoracic cavity increases, causing intrapulmonary pressure to fall below atmospheric pressure. This is also known as a negative pressure. Since air moves from areas of high to low air pressure, air flows into the lungs. Notice that at the end of inspiration, when the intrapulmonary pressure again equals atmospheric pressure, airflow stops. Click the lung to observe intrapulmonary pressure changes during expiration. Observe the changes on the pressure gauge and the graph.
Our voice is very low, and when we bring our vocal cords very close together, our voice is higher. When you cough or bear down, you close this space, closing the glottis, and that increases abdominal pressure, and that happens instinctively during bowel movement and during childbirth. So that leads us to the lungs. The lungs are triangular shaped. Well, I should mention one more thing, and that is the trachea. The trachea is this structure that connects the larynx to the airways leading to the lungs. So this is the trachea. It has C-shaped cartilage to hold it open. But when you get to the lungs here, they're triangular organs. So the base here sits on the diaphragm, and the apex is this pointed region at the top. So each lung has an apex and a base. And this muscular sheet of tissue here is the diaphragm. So I'll look at the picture here of a model. Bear with me, we have a couple of extra slides in this photo. But okay, so here is the a lung, and we can see it's pointed near the top, wider at the bottom. Here's the diaphragm. This sheet of muscular tissue here is the diaphragm. And then the hilum, here the front section of the lung has been removed, but we can see the back section, this orange is all lung tissue, and we can see that there's
intrapleural pressure is the pressure within the pleural cavity. Intrapleural pressure is always negative, which acts like a suction to keep the lungs inflated.
This is the region called the hilum.
The negative intrapleural pressure is due to three main factors: the surface tension of the alveolar fluid, the elasticity of the lungs, and the elasticity of the thoracic wall. Click the alveoli to observe the effect of surface tension. The surface tension of the alveolar fluid tends to pull each of the alveoli inward and therefore pulls the entire lung inward. Surfactant reduces this force. To see the effect of its elastic tissue, click the lung. The surface tension of the alveolar fluid tends to pull each of the alveoli inward and therefore pulls the entire lung inward. Surfactant reduces this force. To see the effect of its elastic tissue, click the lung. The abundant elastic tissue in the lungs tends to recoil and pull the lung inward. As the lung moves away from the thoracic wall, the cavity becomes slightly larger. The negative pressure this creates acts like a suction to keep the lungs inflated. Click the thoracic wall to observe the effect of its elasticity. The elastic thoracic wall tends to pull away from the lung, further enlarging the pleural cavity and creating this negative pressure. The surface tension of pleural fluid resists the actual separation of the lung and thoracic wall. Click the structures to view these forces again.
That's when you get that violent coughing reflex. It's right at the base of your trachea. Again, this region here is called the carina. So then these airways divide, and they divide into primary bronchi, one serving each lung. So this first
Let's watch the intrapleural pressure change during breathing. Click the lung to see these pressure changes. Observe them on the pressure gauge and the graph.
Here, and another secondary bronchi here, and another secondary bronchi here, one for each lobe. Here's a secondary bronchi here, and here's a secondary bronchi. And then these
as the thoracic wall moves outward during inspiration, the volume of the pleural cavity increases slightly, decreasing intrapleural pressure. As the thoracic wall recoils during expiration, the volume of the pleural cavity decreases, returning the pressure to -4 or 756 millimeters of mercury.
Into these smaller segments, which are called bronchopulmonary segments. So each lobe is further divided into these colored sections called bronchopulmonary segments. So not only do you have to know that there's different lobes, but the lobes are further divided into those segments. And
what do you think will happen to a lung if you cut through the thoracic wall into its pleural cavity?
If we look at our dividing tree, we have the trachea, when they have the primary bronchi, then we have the secondary bronchi, and then when we look at those that divide each lobe of the lung, that is called the tertiary bronchi.
Air enters the pleural cavity as it moves from high pressure to low pressure. This is called a pneumothorax. Normally, there is a difference between the intrapleural and intrapulmonary pressures, which is called transpulmonary pressure. The transpulmonary pressure creates the suction to keep the lungs inflated. In this case, when there is no pressure difference, there is no suction and the lung collapses. Click the other lung to discover why it did not collapse. The lungs are completely separate from one another, each surrounded by its own pleural cavity and pleural membranes. Therefore, changes in the intrapleural pressure of one lung do not affect the other lung. To see the effect of pneumothorax again, click the collapsed lung.
End of the respiratory tree. So here's a nice diagram. Shade that in to make that a little easier to see.
Let's review all the events that occur during inspiration.
We reach what we call the bronchioles.
The upper graph shows the intrapulmonary pressure, that is, the pressure within the lungs. The middle graph shows the intrapleural pressure, the pressure within the pleural cavity. The region between the two graphs is the transpulmonary pressure, the pressure difference between the intrapulmonary and intrapleural pressures. The lower graph shows the volume of air which enters and leaves the lungs during quiet breathing. This is called the tidal volume. During inspiration, the diaphragm and external intercostal muscles contract, increasing the volume of the thoracic cavity. This causes the intrapleural pressure to become more negative, which increases the transpulmonary pressure, which causes the lungs to expand. The expansion of the lungs lowers the intrapulmonary pressure below atmospheric pressure. Air, following its pressure gradient, now flows into the lungs. As you watch the graph, notice how the three pressures change together.
Alveolar duct, and then all the little circular structures, those would be the alveoli. And that's where, like I said, where gas exchange
During
takes
expiration,
place.
the diaphragm and external intercostal muscles relax, decreasing the volume of the thoracic cavity. The intrapleural pressure becomes less negative, the transpulmonary pressure decreases, and the lungs passively recoil. This increases the intrapulmonary pressure so that it rises above atmospheric pressure. Air, following its pressure gradient, moves out of the lungs. Watch how the three pressures change together on the graph.
I don't see a number on it, but that's what's shown in beige here. We already talked about those structures.
Let's correlate the graphs with the movements of the thoracic cavity during inspiration and expiration.
You can identify some of these structures on a pin model. And that concludes our discussion of the respiratory system.
Two other important factors play roles in ventilation. These are the resistance within the airways and a property of the lungs known as lung compliance. We will explore these factors individually. As air flows into the lungs, the gas molecules encounter resistance when they strike the walls of the airway. Therefore, the diameter of the airway affects resistance. Let's explore this relationship further. What do you think will happen when the bronchiole constricts? Will resistance increase or decrease? Choose your answer and then watch the bronchiole. That's correct. When the diameter decreases, the resistance increases because more gas molecules encounter the airway wall. Now predict the effect of the increased resistance on airflow. Correct. Airflow is inversely related to resistance. This relationship is shown by the equation airflow equals the pressure difference between atmosphere and intrapulmonary pressure, divided by the resistance. As the resistance increases, the airflow decreases. By the same token, as the resistance decreases, the airflow increases. In healthy lungs, the airways typically offer little resistance, so air flows easily into and out of the lungs. Several factors change airway resistance by affecting the diameter of the airways. They do this by contracting or relaxing the smooth muscle in the airway walls, especially the bronchioles. Click the nerve and the droppers to see how they affect airflow. Parasympathetic neurons release the neurotransmitter acetylcholine, which constricts bronchioles. As you can see in the equation, increased airway resistance decreases airflow. Histamine, released during allergic reactions, constricts bronchioles. This increases airway resistance and decreases airflow, making it harder to breathe. Epinephrine, released by the adrenal medulla during exercise or stress, dilates bronchioles, thereby decreasing airway resistance. This greatly increases airflow, ensuring adequate gas exchange. Another important factor affecting ventilation is the ease with which the lungs expand, also known as lung compliance. It is primarily determined by two factors: the stretchability of the elastic fibers within the lungs and the surface tension within the alveoli. Click the first balloon to see a demonstration of the importance of elastic fibers. This balloon, which is made of thin elastic rubber, inflates easily with a minimum of pressure. Thus, the balloon has high compliance. Healthy lungs have high compliance because of their abundant elastic connective tissue. Now click the second balloon. This balloon, which is made of stiffer rubber, is more difficult to inflate. Thus, the balloon has low compliance. Low lung compliance occurs in some pathological conditions, such as fibrosis, in which increasing amounts of less flexible connective tissue develop. Click either person to repeat the demonstration. The second factor affecting lung compliance is surface tension within the alveoli. See if you can predict the effect of surface tension on lung compliance. Some premature infants do not produce surfactant. Is their lung compliance high or low? Correct. Without surfactant, alveoli have high surface tension and they tend to collapse. Collapsed alveoli resist expansion, so lung compliance is low. This condition is known as respiratory distress syndrome of the newborn. Natural or synthetic surfactant may be sprayed into the infant's respiratory passageways. Surfactant lowers surface tension and increases lung compliance. Here's a summary of what we've covered. Muscle activity causes changes in the volume of the thoracic cavity during breathing. Changing the thoracic cavity volume causes intrapulmonary and intrapleural pressure changes, which allow air to move from high pressure to low pressure regions. Airway resistance is normally low, but nervous stimulation and chemical factors can change the diameter of bronchioles, thereby altering resistance and airflow. Lung compliance is normally high due to the lungs' abundant elastic tissue and surfactant's ability to lower the surface tension of the alveolar fluid.
To access cross-references for this topic in your